Happy Monday, everybody. Welcome back to East 280. Where is everybody? What's going on with 203? Is there an exam? I'm deeply sorry for all of you. But thank you for coming to class even when you have a 203 exam. All right, we are actually going to get started. Stick with me. We're going to get started. I have no announcements. Do you have any questions? Then let's talk about iterators. Let's talk about iterators. All right. So an iterator lets us traverse a container. It lets us walk through a container. We've seen something really similar with arrays. Using integers to visit each item in an array is the same conceptual idea as iterators. This works fine for arrays. It works fine for vectors. But can we do this with our linked list? No. But are you with me that it would make sense, or it would be really convenient if we could visit each item in the linked list? Yeah. So we need some other way to do it. By the way, this is called random access. That's the computer science term. You can pick out anything in an array and get it right away. Is that true of a linked list? No, that's a big difference between these two data types. OK, back to iterators. We're going to use two kinds of abstraction to get this job done. We're going to use procedural abstraction and data abstraction to iterate over a container. So we're going to pull together a lot of concepts that we've used in class already this semester. I'm going to use the templated linked list. Well, I'm going to use a templated linked list for all of our examples today. This matches the linked list that's in your project. It's different than the linked list from lecture because, from the most recent lecture. The only way it's different is that it's templated. So now instead of int list, it's just list and it holds anything you want. This is an uncomplicated transformation to use the template. It follows the lecture we had on templates in the past really closely. And it matches your project exactly. So this list, we can push stuff on the front. We can see what's there and print it. We can pop stuff off and then check if it's empty. Questions about how to use the linked list that we created last time?
Does this one go forwards and backwards?
Does this one go forwards and backwards?
Next and previous?
Does it have next and previous? For today's lecture, what we're going to implement works for both. No, actually, I'm only going to use the forward. I'm only going to mess with the forward pointers. I'm not going to touch any previous pointers. I'll leave that to you for your project. That also keeps the slides a little bit simpler. Where did I get the what? 3. The 3. That is a typo. Thank you. Let me write that down. I can't get away with anything. No, my slides, I want them to be exactly correct. I want you to be able to copy-paste my slides, compile them, and get the same answer. So I really care about getting this right.
It's a comment, though. It would have compiled and worked just fine.
It would have compiled and worked just fine. It would have gotten the wrong answer. All right. So here's where we're going. Focus on this part. This is what we have done using traversal by pointer. This is one of the reasons I wanted you to learn traversal by pointer. Remember, instead of an int, we create a pointer variable. The pointer variable starts at the beginning, keeps going while it's less than the end. And this is pointer arithmetic. What does this pointer arithmetic do to our pointer? Does it go to the next address or does it go to the next integer? The next integer. And then does this give me an address or does this give me an integer object? Integer object. All right. We're going to do something that's a lot like this, but for a linked list. So we're going to create an iterator that starts at the beginning, and we're going to keep going until we are at the end. We're going to move to the next item in the list, and then we're going to access the item. You see how not all of the syntax is the same, but most of it's the same? For example, this is exactly the same. This is exactly the same. This is a really similar idiom. And this is closely related, but not exactly the same. So really what we're going to do is we're going to make a class. We're going to call it iterator, and then we're going to dress it up in a pointer's clothes. That's the rest of the lecture. Yes?
Is this the same thing that we use in the STL libraries?
Is this the same thing that we use in the STL library? Yes. And by the end of the lecture, I'll show you how this works seamlessly with the other STL library stuff. So this is for real. This is how it actually works. And you'll be able to use C++11, range 4 with this and all the toys. Fully interoperable. All right, so now let's do it again. Same code. Let's explain it with pictures. So we start here. We have a list like from last lecture. It's the simpler version of the list that has a first pointer, and it's only linked forward. We're keeping it simple today. So this list is 2, 3. Now here is my variable I, and I points to not a node, I points to a datum. You can think of I pointing to a datum. Again, this is a class dressed up in a pointer's clothes. I points to a datum. Then when we do this, it moves over. It's not a next door neighbor because this is not an array, but somehow we got to get the logic in there to make it do that. And that's what we're going to code today. Questions about where we're going with this?
How do you deal with the last element?
How do you deal with the last element? I'm getting there. We will totally cover that. More questions? Yeah.
Might not be exactly related, but could you overload the square bracket operator?
Could you overload the square bracket operator? Yes. Are we going to cover that today? No. Happy to talk about it later. So we're going to write 4 functions. We need to be able to create an iterator. We'll use a constructor to do that. We need to get the item that's at the iterator's current position. T in this example is an int. We need to move the iterator to the next position, and we need to compare 2 iterators. It's helpful to think about the functions with the color coding and like where they show up in the code. One of the things that's the most confusing about iterators is this nutty syntax right here. The thing that's easy to understand about iterators is it just goes like in order through the list. That part is easier to understand than remembering this syntax. So put this syntax on your cheat sheet for the final exam. All right, we're going to use operator overloading today. Remember, that lets us customize what happens when we use a built-in symbol. We did operator overloading several times in the past. One example was the overloaded assignment operator. We overloaded the assignment operator because we wanted to customize how to make a copy. We did that for a list. We did it for a set. We can overload other operators. What's another example of another operator you've overloaded in one of your projects in EEX 280? The extraction operator. What else? Cout. The oh man, I keep thinking like a C programmer. The bit left shift operator. That's well, actually, yeah, it's overloading the bit left shift operator to do output, which makes no sense if you're a C programmer, and it makes perfect sense if you learn C++ in a 100 level programming class. So they were like, "Here's how you do output," and you're like, "Oh, okay." That's just as weird as typing printf. You're like, printf what? Like print? Should just call it like that. Okay, never mind. So we're going to have two classes for this implementation. One is the list class. That's what we're reusing from last lecture, and it holds the T's. That's our container. The other is an iterator class, and the iterator class is going to return each item one at a time. So now we got two problems already. For the iterator to do its job, it needs to have access to the node type, because somehow the iterator needs to hop from node to node. You with me there? Somehow it needs to hop from node to node, so it needs to know what's inside a node. Also, the iterator needs to return a T. So not just any T, it has to be the exact same T that lives in the list. So iterator and list have to agree about what's a node. Iterator and list have to agree on what's a T. We can solve both these by putting the iterator class inside the list class. Notice how it's public, it's inside the list, and it's a type. This is sort of like, remember when we declared a node type inside of the list? I'm not making a member variable. That's what I want to stress here. I'm not making a member variable. I'm describing a new type. And it's a type that lives inside of the list source code. That's why on this slide right here, that's why we use the 2 colons. Yeah? How is it different than making a separate class and having it derive? So like, let me rephrase your question a little bit. Why did you choose this instead of choosing to do inheritance? The reason I didn't do inheritance is because of the is-a relationship. Inheritance is good for when you can truly say an isosceles is a triangle, a chicken is a animal. That's a good opportunity to use inheritance. This is like a list and an iterator. They're going to be like friends. They're not is-as. They need to know a lot about each other, but it's a different kind of relationship.
This might be covered later, but the type T, if there's two, say we were trying to find an int in the iterator, and there were two ints, two different int variables in the iterator, would it be able to distinguish, or would you choose the first one?
I don't understand the question.
Okay, I guess.
Maybe you can show me an example afterwards. Templates are really flexible. You can do some crazy things with templates that we're not going to cover. So now we need a concrete representation. In other words, we need member variables for iterator. Iterator only has to do one thing, or only has to remember one thing. Iterator only has to remember where am I. And where am I is an address in memory. So we'll use a pointer to a node that helps the iterator remember where am I in the list. So iterator has one member variable. It's a pointer to a node. Here it is in the source code. Notice that this is inside of the iterator. Just a reminder, I am not changing the list. I'm adding code to it. More questions so far?
When you create a new iterator and we have code inside the constructors, does it show both, or does it just show instructor CTOR? Would it show the CTOR as well since it's inside, or no? I don't think so. Right?
I don't understand the question.
Yeah, no.
Okay. We need some member functions. This class is still inside the list. I'm just displaying a subset of the code on the slide. So here's a constructor for creating it. We're going to overload the dereference operator. We're going to hack the star symbol. We're going to hack the plus plus symbol. And we're going to hack the not equal symbol. So we're going to make these things do custom stuff only for an iterator. Not just any iterator, the iterator that lives inside the list. So let me remind you where these came from. Or rather, let me remind you where we use these functions. So this green code is the constructor. Keep in mind that to describe the type, you need all of that. Because which iterator? Oh, it's the iterator that's inside of the list. Well, what kind of list? A list that holds ints. The compiler needs to know about all of that to know which type you are talking about. So everything in the red box is one type to the compiler. It's one type.
Can we use auto because it's C++?
Can we use auto? I will show you how to use auto at the end of lecture so that you never have to type this again. And I guess now that I think about it, we'll allow full C++ 11 on the final exam. Well, you should still type this because we could print code that looked like this. So now we're going to implement the methods. We know what the pictures should look like. We know what points to what. Now let's implement them one at a time. We need a constructor for iterator, and we need to create an iterator that is a default value. We're going to make an iterator that's a default value. This is a design decision that all the standard template library containers obey. And that is that a default iterator points one past the end. So here's the way to think about it. This list points to null PTR. That's a way to think about the 0. And the null PTR is like somewhere off in memory. This iterator also points to null PTR. Null PTR is one past the end of the container. One past the end of the container. So we're going to implement these functions in line. We don't need any more code. We're setting the one member variable to null pointer, aka 0. All right, we just wrote our constructor. Now let's implement the dereference operator. Please write this function. It might help if you need a hint. Look at the first few pictures I showed in lecture about what points to what. Let's take a look. So we have a list like this. And if we have I that points here, I points to the node, right? Not the datum. Is this function supposed to return a node or a datum? Okay, datum. Do we want an address of a datum, or do we want like a value or reference? Value or reference. A value turned into the reference, like that. So we can return node PTR. So I has a node pointer in it, and that's what this pointer is. How do I find the datum? With the arrow. And that's it. Oh yeah, we can be extra safe too.
If we wanted to, could we just assert node PTR?
Say that again?
If we wanted to, could we just assert node PTR?
If you wanted to, could you assert that, and would that be the same code? Yes. Those are equally correct. All right, everybody with me so far? So work with me here. Writing iterators involves, the most complicated part, I think, is the syntax. The syntax is really confusing. The concept of like dive into that pointer and give me the datum makes more sense than why did you use all those stars and ampersands. Assertions always help us find bugs in our programs. This one will help us figure out if we accidentally went past the end and then tried to look at what was past the end. I mean, I know we talked about null PTR being at the end of the rainbow, but we'll never actually find out because we can never actually see what's there, at least with an iterator. So the node pointer points to a node that was created by the list. And why does the iterator have access to the members of the list? Because the iterator is a different class and a different type. So the iterator has a pointer to a node, and the node's data members are all public because it's a struct. So if you have a pointer to it, you can access what's inside. And the iterator is a member of list. The node is a member of list. So the iterator knows about the node and like what that type is. So you put all those things together, and that's how the iterator can access the node's internals.
You said the iterator was a class definition and not a member, so could you maybe like reword what you said? Could you just say that the iterator was a member of the list?
So the iterator definition is a member of list. The node definition is a member of list. So the iterator source code has access to the node source code. So when the iterator source code does this, the iterator source code knows what is supposed to live inside of a node and how to find it.
If we did not include the ampersand in the signature of the function, would that return a value instead of
The question was, what if we did this? Then we'd return a copy of a datum instead of the home of the original datum. So would that work for reading a datum?
Yeah.
Yes. Would that work if you wanted to use an iterator to change a piece of data? Agree, it would not work to change a piece of data. So now we're going to move on to the next, implement the next operator, the plus plus operator. This is the prefix increment. So just keep in mind, we are implementing this, not that. You could implement the postfix operator, and it would be slightly different. And I'm not teaching that in class today. Actually, an aside, remember when we talked about prefix versus postfix, and it's only use postfix if you want to do two things on one line and be queued at the same time? You will learn, if you try to implement postfix increment, you will learn why you should only use it when you really want to. The implementation is a lot more complicated. You have to like make copies of yourself and do like swapping yourself so that it does the right thing. Okay, back to prefix increment. Our goal is to make this thing move so that it points to the next datum. Your turn again. All right, let's take a look. So let me ask you, is this going to do it? Would this go to the next door neighbor in memory? Yeah. Is the next door in memory something we care about? No. So instead, we're going to use the next pointer to slide forward one node. Then, before we do that, we should check that we're not already at the end. This will be a little sanity check to crash the programmer's program if they try to like whiz past the end and then keep going. Okay, why am I doing return star this? Because I need to return an iterator. What's the type of this? Pointer to iterator, or iterator pointer. What's the type of star this? Iterator. And does that match the type I'm supposed to return? Yeah. So here's where it would be helpful. So you can do really cool things like that. Which works.
Why can't you just return node PTR pointer next?
Why can't you return node PTR pointer next? Like, because that would be the next one. You could do that, and it would be a really hard to find bug. Yes?
Why do we need to return an iterator since we're only essentially just...
Why do we need to return an iterator? Okay, imagine you returned nothing. Imagine it was a void function. Would this code work right here? Yes, it would, because it doesn't need to output anything. Now, would this code work? No, because step one, do that. If the output was void, then what would you assign? If the output was iterator, then what would you assign? Well, the thing you just incremented. Same thing here. What should I increment next? Oh, the thing I just incremented. That's why returning references makes it possible to do two things on one line.
How does the compiler know that we're only overloading the prefix operator, not the postfix operator?
Oh, this is a nasty question. Disgusting. How does the compiler know the difference between operator plus plus and operator plus plus? This is a disgusting answer. Are you ready? A dummy input. It's an input that's never used, ever. The only reason it's there is to tell the difference between the two. It's horrifying. And it's part of the C++ standard library.
Is memory allocated for the W variable?
Is memory allocated? I actually don't know. That's a good question. And what would you get if you gave it a name and looked at the value? I have no idea. You could try it though. Yeah.
So if you try to use a postfix operator, would it try to execute what you overloaded?
So the question was, let's say we tried to use, let's say the code looks like this, and we tried to use postfix increment. The compiler would be like, oh, I don't know what you're talking about. There's no function called postfix increment. And indeed, there is none because we didn't provide one. I know the syntax is getting pretty complicated here. Can I answer more questions about it?
So, I know you said that we could return node pointer to next, but could you return just node pointer after you had set node pointer equal to node pointer then?
Could you return
'Cause, I mean, that would be a pointer, but
node pointer?
yeah.
Could you return node pointer instead of this, like star node pointer? I think so. I don't know the answer to that. I'd have to try. They should point to the same place. Star this, it is idiomatic. Like all prefix increment operators, they look kind of the same. They have a lot in common. So once you implement one of these iterators, the next one is a lot easier because you can copy paste a lot of the code and the syntax. So now we need to compare. For this, we're going to overload the not equal operator. So think about how we're going to do this. Are you with me that if a pointer points to a node and another pointer points to the same node, they must point at the same thing? Okay, so then that's what we'll do. So here's what's going on. We're going to compare this iterator right here against the iterator that is an input, the iterator on the right-hand side. If they point to the same place, they're equal. If they point to different places, they're not equal. This is one of those tricky things that is hard to remember but consistent. The input is the right-hand side. This is the left-hand side. Where did we see that in the past? In the copy constructor we saw it, and we saw it in the operator equal, the overloaded assignment operator. That's another example where there were two things involved. One of them was this, and the other one was the right-hand side. So weird to remember, but consistent.
I don't understand the not equal. The node pizza are not equal to R. Like, what does that mean exactly? I know it's, what does it mean?
So what's going on here? First, we look at the address of where the first iterator points to. Then we look at the address of where the second iterator points to. If those addresses point to different places, then they must be different iterators. That's the logic we're using. So this is where we use them. When we're comparing the iterator, that's this, against the right-hand side. Okay, so Now we can create iterators, get the item that the iterator is positioned at, move the iterator, and compare two iterators. What are we missing? We don't know where to start, and we don't know where to stop. So the iterator points at nodes, but how could the iterator possibly know where the beginning of the list is? That's the list's business. So we'll just ask the list. The iterator is going to ask the list, hey, where do you start? And the list says, right here. We'll do that in a list member function. Begin, and another list member function, end. That's how you ask the list a question, is with a member function.
Is end just null pointer, or is that from the last?
Is end just null pointer, like one past the end? Yep, so that one's going to be really short.
Then why even have one? Or
Why even have one?
like, why not just have not equal?
Because there's other containers that are implemented in different ways where we really do need to ask the container, where do you end? Like, think about a vector. Does a vector end at null pointer? No, it ends at like a really specific address. So you need an end function to tell you which specific address that is. So it's important that we have an iterator that works for linked list, but also works for all the containers. That's why this is important.
If I remember correctly, the start and end member variables in our list are node pointers, but you're assigning that to an iterator.
So we haven't written the begin function, and we have not yet written the end function. When we write those functions, we'll pay attention to the member variables and like whether they're pointers and what types they are, and we'll get our types right. So end is a list member function. That's why we are now in the list class. Because again, only list knows where it starts and ends. In this case, it's a simplification. You pointed out earlier, like, hey, we already got a default iterator. And so list is like, well, yeah, okay, I'll just return this default created iterator, which points at null pointer, which is the same thing as 0. So more fancy syntax, but with small quantities of code. Each of these functions have been like 1, 2 lines of code. Can I implement the begin function? Or do you need another minute with this slide? All right, on to the begin function. So the list knows where the list begins, right? It's a pointer. And that pointer is called first. So all we got to do is create an iterator that points to the same place that first points to. Cool. So how about we make a new constructor that creates an iterator with the node pointer set to a specific value? Are you with me that we could overload the constructor and we could do this if we want to? Okay, so let's do that. So we're going to go back inside our iterator class, and we'll implement this custom constructor where the input pointer is stored as the member variable. So now we can create an iterator that points to wherever we want. Uh-oh, we got another problem. This is a private member function. Okay. Is the outside world going to use iterators? Yeah, the whole point is for other programmers to be able to walk through the list. So should the other programmers be able to use a bunch of public functions? Yes. Should other programmers know about nodes? No. So that's why this is private. But wait a second, if it's private, then how is the list going to use it? Do you see how I'm in a catch-22? Did you say no? Oh, you had said yeah. So list needs to access the constructor, but it's private. We don't want other programmers outside the list to access it, so what do? So we have a bad solution, which is make it public, but then other programmers know about the node. All right, we're going to introduce a new C++ concept to solve this problem called friend classes. A friend declaration lets you expose the private members of one class to another class. So this is iterator exposing itself to list. Yes? Could you do that even if it wasn't nested? Yes. You could do this with any other class. So now, this is private, but we're friends. To remember how friend works, just remember that friendship is something that is given, not taken. So this is like iterator giving consent to show its private parts to list. I know, right? So now list can touch iterator's private parts. Just to be very specific. So that means if you want two classes to touch each other's private parts, they both have to friend each other. So you need to use the word friend twice in your source code. It doesn't sound like this is a friendly relationship. Yeah, this is more of a business relationship, I guess. But it's best to use friend just enough to get your code to achieve the access that you're looking for. So I will review this. I know we went through a lot. I will review this after we take a break. So let's take a break. Again. So today is equinox, I think. The days are almost equal to the length of the nights. So my chickens are getting really excited to spend more time outside. When there's more sunlight, they lay more eggs. But right around this time of year, the other animals have been really hungry from a long winter. So the raccoons and the possums are trying to eat my chickens. The other morning, I went out there, and usually I like open the door and I let them like run around outside while it's light out. And usually other animals are not going to try to kill them when it's light out. They wait for night. So I get out there. It's like just at dawn, and there's a possum scratching at the door to the chicken coop. And possums are like, they kind of look like giant rats, and they got all these teeth on them, and they go like this. So I grew up in the suburbs, and I don't know a whole lot about what to do with possum problems. My wife grew up on a farm, so I went inside and I like woke her up, and it's like, we got a possum that's trying to kill our chickens. What should I do? So mind you, she's a vegetarian. She was like, kill it. So I'm like, I live in downtown Ann Arbor. And she was like, well, Daddy uses the shotgun and Mommy uses the shovel. You decide. So I'm sitting there and I'm like, well, I'm just going to end the story there. So let's go back to our iterators. I am going to recap all the code we just wrote. I know it's pretty confusing syntax, and it's helpful to see it a second time. So we're adding code inside our list class. We haven't taken any code away, and we haven't changed any of the code we wrote last time. So all of those member functions and all those member variables are still there. We're adding a new type. That new type goes inside the list, and it goes inside the public part of the list, because we want other programmers to use this iterator. This iterator stores a pointer to the current list position. The current list position is some node somewhere in memory. We need a way to create iterators. So the default constructor creates an iterator which points past the end of the list. We're making a class that's dressed up in the clothes of a pointer. So part of pretending to be a pointer is to be able to do dereference. This function lets us use the star operator, the dereference operator, on a variable whose type is iterator. The main goal is to return a value. That value should match this type. So we look inside the node that node pointer points to. We pick out the piece of data, and we return it to the other user, the other programmer. Please interrupt me while I'm going through this review. I'm happy to answer questions a second time. Or new questions as you're seeing the code for the second time. That's what I meant.
How do we know when we need to use the T, the template?
How do we know when we're supposed to use T, and how do we know when we're supposed to use int or iterator or some other type? So we know that the list is a container, and containers are supposed to hold other types. So when we want to say, all right, right now I care about the type that the list is holding in its container. When that's what I want to express, that's when I use T. So dereference, the goal is to say, all right, I know this iterator points somewhere. I don't really care where it points. I just want the thing that lives inside the list, the thing that it's pointing to. So that's why we use T.
So both the iterator class right here, would we have to include type name?
Do we need to include type name? So template type name T is here above list, and that applies to list and everything that lives inside list, including iterator. So that solved our problem of like which T is which. We also need to move the iterator to the next node in the list. That's the prefix increment operator to move we go node pointer arrow next. That's the important line of code here. We also need to compare two iterators. That's the operator, the not equal operator. To compare two iterators, we compare the things that they point to. We compare the iterators they point to. If the node pointers are different, then the iterators are different. If the node pointers are the same, then the iterators are the same. That's what this code is doing. Then we need to construct an iterator at a specific position. We do this so that the list can tell the other programmer where do I begin? The list is like, I'm a list, and I begin at this iterator by converting a node pointer to an iterator. It's only for internal use, so it's private. But oh no, the list is supposed to use it in the begin function, but it's private. So the iterator will say, no, it's cool. You can be my friend, and that means you can access my private member variables. Friendship is something that's given, not taken. So the friend goes inside of the iterator. The end function, remember this is inside a list, is a default iterator past the end. Okay. It took an hour, but now it took an hour to write what was basically 4 to 6 lines of code wrapped up in a whole lot of crazy syntax. But now we have a list and an iterator that work just like the standard template library. So we can create a list and push some stuff into it. And then we can use this code, which is exactly like the code you would use with the standard template library list or other containers that are in the standard template library. And you can print the items in the list. You can not just print them, you can do whatever you want with them. You can visit each one at a time. Now let me tell you how to avoid this nastiness. Are you ready? This is why C++ 11 is amazing. Because of that. All right, keep in mind, we're using the custom list. This is the list that we coded over the last 2 lectures, including the custom iterator. We're using the auto keyword and the range for operator. So range for, now I can explain what it actually means, since you will understand. Now that you know iterators, you'll actually understand what it means. Range for is syntactic sugar for start at begin and end at end. So you can imagine what range for is really doing is copy pasting all of this code. Super helpful. I got one difference. Notice here that we had to be careful to dereference our iterator, because we care not about the iterator, we care about what the iterator points to. Range for, this is a value. It's a T. It's a datum. This is a difference between range for and using the iterator directly. So range for is like, please visit by value.
When you say range for, are you referring to the word auto?
When I say range for, technically I'm referring to the colon. It's almost always used together with auto. So in other words, doing it like this, these go together most of the time.
Still a name for a for each loop?
Is this another name for a for each loop? For each is something else in C++ that's kind of a pain in the ass. C++ 11 is so much easier than using for each from the standard template library that everybody does this now. But before C++ 11, for each was another way to do it.
In order to use this, do we need to name, do we need to code begin and end?
So the question was, for this to work, do we need to have a function called begin and a member function called end. Yes. Let me go even deeper than that. For this to work, you need a begin member function. You need an end member function. They need to return objects that do prefix, increment, dereference, and not equal. Oh, wait, we just did that. So as long as you have those member functions, it works.
You have to be named begin then.
They have to be called begin, open parenthesis, close parenthesis. Yeah, exactly that, and returns nothing.
What does the keyword auto do, and what does the one after the colon do?
Oh, this is an L. I should go through this whole lecture and change all my L's to like something else.
Okay, so that
Else? So here's what auto does. Int I equals 0, auto I equals j. What's the type of I? I'll give you one guess. Int. It basically like mimics types. It's like, give me the type that's the same as that other thing. Auto means give me the type that's the same as that other thing.
Can you explain why you don't have to put the star for the for the CR?
Why don't you have to put the star here?
Like it just does it for you? Or?
Because it does it for you. Range 4 does it for you. Oh, I made a mistake here. Thank you. Auto j is equal to I. Make a new type, or sorry, make a new variable called j, and its type should be the same as the thing on the right. Thanks for the correction. If we could just use auto, so I'm going to rephrase your question a little bit. Why did we go to all the trouble of implementing our iterator with that special asterisk syntax and that special not equal symbol and that special prefix and all that special stuff that gave us such painful syntax? Here's why. When you use range 4, it's copy pasting plus plus and it's using not equal and it's using star. So any iterator that does star and not equal and plus plus will work with range 4. We did it all for the range 4. What if your node has more than one datum? What about it? What would the value of I be? Oh, if you have more than one datum, you just package them up inside of a struct. And then two become one. This is a very sexy lecture today. Okay. So now we're going to use iterators. And I'm going to show you all the things that can go wrong with iterators, or as many things as I can think of in the next 20 minutes. So now we can write functions that use iterators, and now those functions will work with any container because the containers all have iterators. So if we changed our mind about like a vector or a list or a set or something else, we can still use the same algorithm. And since the iterator is an object, we can have more than one pointing to the same list. I'm going to start using auto, and I'm going to stop using that long name of iterator list int : iterator. So we can make a list, we'll fill it up, and that's L. Then we can create two iterators. And we can move one of them. So let's walk through this code one step at a time with pictures. So we start off with a list that has two nodes in it. That's the first line. I skipped the code with the pushbacks, okay? But there's some push fronts in there. Then I get an iterator type. Everybody with me on the auto usage of auto here? Then I use auto again, and it's like, give me the same type that's on the right. So I get two iterators that point to the same node. Then I move one of them forward, like that. And then I print I print I, and I print j, and I get I points to 2 and j points to the node that points to 2.
Can you have an auto reference variable?
Can you have an auto reference variable? You sure can. So we could do that.
Wait, the begin returns an iterator, right?
The question was, does the begin function return an iterator? Yep, the begin function returns an iterator, and that's why i's type is iterator. Again, auto mimics the type on the right. So why are you dereferencing I and j? I thought auto did that. Auto doesn't do that. Range 4 does that. And you sort of accidentally mixed up that range 4 and auto a lot of times are friends and go together. They hang out together a lot, but you can still use them separately if you want to. Yeah.
Do we have to hashtag include anything for auto? Or
Do we have to hashtag include anything?
is it just...
No, yeah, I just need to let that sink in for a minute. I don't know. What's a hashtag? What's a good hashtag?
Not my president's show.
I'm not going to get into politics in computer science class. Hashtag pound sign? Oh, geez. Okay. What? Hashtag,
You have
hashtag.
to write the last one.
Oh, wait. Hashtag. Okay. Hashtag, hashtag, hashtag. We're going to talk about recursion in the future, actually. So, I forgot where we were going with this. What was the question? Do I need to pound include anything for auto? No, because it's built into the C++11 language, not the library. It's built into the language. All right. I don't think we have, I'll give you a couple minutes to think about this one. Probably not enough time to actually finish it. Think about where you would need to use where you would need to make modifications to this code to convert it to use iterators. Okay. I realize you probably did not have enough time to finish this. That's okay. I want to make sure we have enough time to get through the rest of the lecture today. So did anybody notice that range 4, you run into some complications if you try to use range 4 here? The complication is, well, what if you want to play around with exactly where it starts? Does range 4 let you change where to begin and where to end? No, it's everything. It starts at the beginning and it goes through everything until you get to the end. That's the only option. So if that's not what you want, then you can't use range 4. We can still use auto. This is, again, what I was just explaining, the wrong answer. Because if we use auto, j and I are integers. But we don't want to increment the integer. We want to move the iterator around. So for simple visit each item, range 4 is awesome. For more complicated algorithms where you need to play around with the exact positions, like this one, then range 4 is not going to do it. We can still use auto, though. We can just say auto I equals begin, and we can save ourselves the hassle of typing in that long type. So now, when I copy j, I can use my increment operator and slide it forward by 1 spot. So the question was, what if I did j is equal to plus plus I? So I got a question for you. The line of code that I wrote up here, does that move I forward by 1 position? Yes. And does it set j to be 1 step forward, and is that what I want? Yes. Okay. Did I really mean to move I? No, I didn't. So that's a bug. Hey, if we wanted to, we could go back to our iterator and we could implement the plus operator.
In the second or thing, is there supposed to be something before the first semicolon?
The question was, why are you being so forgetful? The answer is, don't tell me what to do. So that's a funny way of saying for loops, the stuff in a for loop is optional. Because j is already good. I mean, I got it. It's right here. I'm confused now. Were you being an iterator that pointed to him? Yeah. Okay.
Could you put the plus plus j in the first part of the for loop?
So if I wanted to, could I do this? Yeah. You can put any code you want in the first part of a for loop. It's just, there's nothing special about the first part of a for loop. The only thing that's special about it is it runs once. For loops, not quite as special as you thought they were. All right, here's a question for you. If for loop was eradicated from the C++ programming language, would it be possible to rewrite all the programs that are out there to still get the right answer? Yeah, what would you do? While. For loops are syntactic sugar. They're like a convenience. And they are convenient. All right. Do we need the big 3? We have a pointer that points to dynamically allocated memory. Sure seems like it. I'm going to let you think about this. I'm going to count to some small number while you think. Maybe like 17. If you think you got the answer, I want you to convince yourself why. So let's think this through together. So let's think back to our list. List, it had a member variable that was a pointer, right? And that pointer pointed to dynamic memory, right? And the iterators got a member variable, it's a pointer, yeah. And that pointer variable points to dynamically allocated memory, right? So it needs a destructor. No. Here's the difference. List had a pointer to dynamically allocated memory that was created by list. And so list had to clean up its own mess. Is that true here? Not quite. So no, because the memory is already managed by the list. So if you allocate memory with new, you need to allocate it with delete. That was true in the list. And that's not true in the iterator, because the iterator did not make its own mess. The iterator didn't make any new messes, so the iterator doesn't have to clean the mess up. All right, let's go through. I think we have enough time for one example. Yeah, we'll go through one more example of things that can go wrong with iterators. So here's something that something complicated that iterators share with pointers. You can create an iterator. If the container is modified, the iterator might become invalid. So that's kind of like if you have a pointer to an array and then you delete the array, does the pointer still point to the same address? Yeah. Is the array still there? No, it's an invalid pointer. Similar things can happen with iterators. So the general idea is if the container under the hood changes, then the iterator could become invalid. So now let's see what's wrong with this code. I will show you step by step with the pictures, and I'll make sure that we get out right on time. So you can relax. So here's our picture, line 1. Fill up our list with 2 items. Then we're going to create one iterator that points to the beginning of the list. Then we move our iterator 1 spot, so we moved it over here. And then we move our iterator 1 spot, which is okay. Now our iterator points at null PTR. Are you guys okay with that one? I know it gets a little tricky when it goes off the end. So our iterator is still sane. It fulfills its representation invariant. It passes the sanity check. Uh-oh. Hey, we did this on purpose to catch our own mistakes. So that's helpful. We caught our own mistake. Well, what if we do this? Remember, you can get rid of the asserts in the production code. Pound define and debug. Then here's what you get. So all I can tell you about this is don't do that. In other words, it's the programmer who uses the iterator. It's that programmer's responsibility to avoid invalid iterators.
So since iterator is pointing to dynamically allocated memory, should we be taking care of any like dangling iterators when we delete that memory? Or
So the question was like,
how do you not do this?
how do you not do that? How do you not do this? Don't go off the end of the list. Unfortunately, there's not a better answer than that. It's your responsibility as the other programmer to stay inside the container. So it's the programmer who uses the iterator. It's their responsibility to stay inside the bounds of the container, even if the container changes. So iterators are kind of like a double-edged sword. Here's like a thought experiment. What if we coded a really fancy iterator that pointed both ways? Like the list knew about the iterator and the iterator knew about the list, and the list would be like, iterator, you're done. And then the iterator will be like, I'm done. I can't do that. Like, why not do it that way? It'd make the program slower. We'd also need to add more source code to check if it's inside the container or not, so the other programmer would have to remember to check. So there is no perfect solution here. Valgrind can help you find these kinds of errors too. One more mistake. All right, same list. We start off again. And then we get a pointer to the first node in the list, same as before. Then we call pop front. Sure, we can do that, right? And then you get then you end up with like another GIF of a dancing chicken, because this is undefined, and when undefined behavior happens, anything can happen, including getting the right answer, or including getting a GIF of a dancing chicken. So be careful. The end.